Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 4, Part 2, Pure Substances, Lecture number 4. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So, we will solve numerical on use of steam property tables. So, let us take this numerical. A steam boiler initially contains 5 meter cube of steam and 5 meter cube of water at 1 megapascal. Steam is taken out at constant pressure until 4 meter cube of water is left. What is the heat transfer during the process? Okay, so you have a boiler wherein initially 5 meter cube of steam and 5 meter cube of water is there. Then steam is continuously taken out from the boiler, and as a final state it is left with 4 meter cube of water. In the sense 6 meter cube is steam. So during the process, what is the heat transferred? So that you have to find out. So this is a diagram. Okay, so this is a complete diagram. Okay, so this is closed part. Don't think it is open here. So it's boiler. Here also it is closed. So initially you have 5 meter cube of liquid water, saturated liquid, and 5 meter cube of saturated vapor. So then your liquid becomes 4 meter cube and vapor becomes 6 meter, because total volume is 10 meter cube. It's understood that Vg is 6 meter cube as the final state. Now the pressure given is 1 megapascal. Pressure given is 1 megapascal, so that is 10 bar. So from the data handbook, so all of you can see that this is what the table I am using, thermodynamic data handbook by VTU Nurgemar and B.S. Samaga. So here table A1, so at pressure of 10 bar. So I have already placed an extract there. So 10 bar pressure. So you can note down Vf 0.11274, Vg, Hf, Hfg and Hg. So these are the values required for me. Even if you calculate, note down other values also, nothing is wrong. So this is how you have to refer the table. So Vf, Vg, Hf, Hfg and Hg values are noted. Now U value, because whenever you have to calculate heat transfer for the steam during any thermodynamic process, so internal energy has to be calculated. Since it is not given, so I calculated here Uf as Hf minus P into Vf. So Hf minus P is 10 bar, so it has to be converted into kilopascal because all these quantities are in kilojoules. So pressure has to be in kilopascal. Very, very important point to be substituted. Pressure should be in kilopascal. Then Vf, so you will get it as 761.57 kilojoules per kg. Similarly, Ug, you can calculate it as Hg minus PVg. Okay, so that is, after substitution you will get as 2581.9 kilojoules per kg. So UFG is nothing but Ug minus Uf, so that you will get as 1820.33 kilojoules per kg. So this calculation of the internal energy using H minus PV formula is very, very important. Okay, once you calculate Uf and Ug, so UFG is nothing but Ug minus Uf, or directly instead of Ug you can calculate UFG also, right? HFG minus P into VFG also you can use, but VFG is nothing but Vg minus Vf. So the initial mass of the saturated water and steam in the boiler you have to find out first. So M1 is nothing but mass of saturated liquid plus mass of saturated vapor. This is saturated liquid mass, this is saturated vapor mass. So this is nothing but mass, total volume of liquid divided by specific volume of saturated liquid. This is total volume of vapor divided by specific volume of saturated vapor. So both the things, you know, total both the volumes are 5 meter cube, and Vf is here divided by Vg is here. So you get total mass of Mf, one as 4434.98 and Mg as 25.73. You keep it as it is. I'll tell you why. Okay, don't add. And final mass of saturated water and steam, Mf2 plus Mg2. So final volume is 4 meter cube for water and 6 meter cube for vapor. So you'll get it as 3547.98 plus 30.88 kg. Again Mf2 and Mg2 is kept separately. Okay, so mass of steam taken out is nothing but the difference of these two. Now you can add and you can find out, because total steam because whatever being is taken out is the difference of mass is nothing but the steam. So nothing like water and steam two phase, no, it's single phase. So 81.5 kg. So this is the mass of steam taken out of the boiler. Now making energy balance. Okay, it's just come as single slide, no problem. So energy balance. So initial energy stored in saturated water and steam plus heat transfer from the external source, because you see there is some internal energy, initial energy is there in the water. Now during this process of conversion of water into steam, so continuously you are supplying heat from the external source. So this is equal to final energy stored in the water plus energy leaving the steam, because already some steam being taken out, 881.5 kg. So along with that some heat is being removed or gone out. So the energy balance is U1 plus Q, that is initial energy of the water and steam mixture plus heat supplied, is equal to final internal energy plus Ms into Hg. So U1 is nothing but Mf1 into Ef1 plus Mg1 into Ug1. Now you can understand so why I kept it as Mf1 and Mg1, because mass of saturated liquid should be multiplied by internal energy of the saturated liquid, and mass of saturated vapor should be multiplied by the internal energy of the saturated vapor. Plus Q is unknown. So final steam Mf2 Ef2 plus Mg2 Ug2. Now here the mass of steam taken out is Ms, and heat carried away by that steam is nothing but Ms into Hg, because we assume it as dry steam. You see, because the condition of the steam taken out is not given, so let us assume it as dry steam, because steam has to be dry if it has to go out. Okay, now making the energy balance, making proper substitutions, all of you can check it. So you will get the Q value as 1785004 kilojoules. I hope my calculation is perfect. Substitution is perfect, formula is perfect, I know. So make proper substitution and check or verify the answer. I hope the answer will be correct. Okay. Okay, let us solve this problem. Steam flows in a pipeline at 1.5 megapascal. After expanding to 0.1 megapascal in throttling calorimeter, the temperature is found to be 120 degrees Celsius. Very good. The problem on throttling calorimeter, which we discussed in the last lecture. So here steam initial pressure is 1.5 megapascal, that is the steam main pipeline, and after throttling or expansion the pressure is 0.1 megapascal and temperature is 120 degrees Celsius. Find the quality of the steam in the pipeline, and also you have to find out what is the maximum moisture at 1.5 megapascal that can be determined with this setup if 5 degrees C of superheat is required. Okay, minimum temperature of or degree of superheat should be 5 degree. It should not be dry, it should be 5 degree above dry temperature. So that is what he is asking. Now let us find out the quality of the steam in the pipeline first part. So at state 1, so 1.5 megapascal, so that is 15 bar. So from the thermodynamic data handbook you can note out HF and HFG. In fact you can use the suffix 1 also, HF1 and HFG 1 also you can use, because it is a state 1. Okay, now this is the extract of the sample I am using here. So 15 bar, so this is 844.6 HF and HFG is 1945.3 kilojoules per kg. Okay. So now let us find out the condition of steam at 2. So at state 2 it is given pressure is P is equal to 0.1 megapascal or 1 bar. So go through the data handbook and you can find that the saturation temperature at that pressure is 99.63 degrees Celsius. But given temperature of steam after throttling or expansion is 120 degrees Celsius, which is greater than Ts, therefore steam is superheated. Mind it, this is very important part of this problem. After throttling, for the given pressure and temperature, you have to check the quality of steam. Sometimes Ts and the given temperature may be same, then it is dry steam. So then you have to go through the dry steam table, you have to find out Hg. Suppose if the given temperature is like this, 120 is more than saturation temperature 99.60 degrees Celsius, then the steam is superheated. Then you have to go through the superheated steam table. Now there is a table A3, which is a superheated steam table in thermodynamic data handbook. So at 1 bar you have to find out the enthalpy. But unfortunately the data available is only for 100 and 150 degree Celsius, there is no data available for 120 because we require for 120 degree Celsius. So let me show you the sample of the table here. You can see here, so absolute pressure in bar bracket saturation temperature, that is 1 bar, and the saturation temperature is 99.6 degrees Celsius. And for this pressure temperature combination, specific volume, specific enthalpy and entropy values are given. So 50, there is no value, 100 and 150 it is given. So 100 it is given, I want enthalpy as 26.76.100 and 150 as 2776.3, but I don't have any value for 120, which I should take it as x. Now x can be found out by using this formula. So you have to take x minus this divided by this minus this. Better you always take any two differences you can take and you have to take the ratio. X minus 2676.2 divided by 2776.3 minus 2676.2. Same ratio you have to take on the other side, that is 120 minus 100 divided by 150 minus 100. So any two differences you can take, but better always take x as ones because simplification becomes easier. So if you simplify this, so x becomes h2, so h2 becomes x is as 2716.24 kilojoules per kg. So this is how you have to find out the enthalpy at state 2 after throttling, but here I required interpolation. Okay. Okay, now this is the diagram. Okay, before that, let us find out the drainage fraction using throttling first part. So H1 is equal to H2. So H1 is HF1 plus X1 HFG1, and H2 is just now you calculated. So you see this is from state 1, this is state 2. If you want you can write bracket state 1, okay, because that is because suffix 1 also indicating that. So HF1 and HFG1, X1 is unknown, H2 just now you calculated. So you'll get X1 as 0.962 as the dryness fraction. Okay, X1 is 0.962, that is the answer. Now to find out the maximum moisture content at 1.5 megapascal for a least of 5 degrees Celsius superheat. So now this is the first part is 1, dryness fraction is here, and this is after throttling, the state 1 is here, sorry. So this is state 2 after throttling. Now minimum dryness fraction should be maximum moisture content you have to find out for minimum of 5 degrees of superheat. So that is condition for state 3, 4 and 3, because it's a new state now. So here for minimum of 5 degrees of superheat, right? So at 1 megapascal, 0.1 megapascal or 1 bar, saturation temperature is 99.63. So minimum of 5 degree superheat means your superheated temperature should be 104.63 degrees Celsius. Try to understand this. Least of 5 degrees Celsius superheat is required. That means from saturation 5 degree above. So saturation temperature is 99.63 at 1 bar or 0.1 megapascal. So plus 99.63 plus 5. So it is 104.63 degrees Celsius superheated. Now at this temperature and pressure condition, once again you have to find out the value of enthalpy. So as I told you earlier, A3 table, but available is only 100, 5 and 150. So you have to do it for 104.63 like you did above. So I am not doing that interpolation part, right? Same previous slide, but here instead of 120 you have to write 104.63, and H3 you will get as 2685.46. Now you have to use the formula H3 is equal to H4. So your H4 is nothing but initial condition 1.5 megapascal or 15 bar, same as H1 values, so same as HF1 and HFG1. So new dryness fraction you have to find out. So that is X4 is equal to 0.9463. That means 94.63% of dryness fraction, that is steam quantity, dry steam quantity can be measured. That means maximum moisture content is 1 minus that is 5.36%. So up to 5.36% of moisture you can measure using this setup if 5 degrees of superheat is required, minimum of 5 degrees of superheat. Okay, that is the condition. So very important to understand that and solve the problem. So with this I conclude this lecture 4. That is the first lecture of on numericals. So we will continue with a few more numericals in the next 2 lectures. Thank you.